Switches and crossings play an essential role in connecting the rail network. We use them to guide trains from one track to another and to enable lines to cross paths. Put simply, they're the junctions that allow us to create a multi-lined, multi-routed rail network. At Network Rail, we own over 20,000 switch and crossing units. They come in many different shapes and sizes, and all are made to measure for their specific location. To understand how switches and crossings work, we first got to look at the wheel-rail interaction. Train wheels move along the rails guided only by the pound-coin-sized area of wheel that sits on the railhead. The wheel rim, or flange, doesn't normally touch the rail. Flanges are only a last resort to prevent the wheels becoming derailed. A switch can guide a wheel in one of two directions. A crossing creates a gap in the rail for the flange to pass through. This is a switch. Also known as a point, it's the moving part of the switch and crossing layout, and is made up of two long blades which can move across to guide the train one way or another. This is the switch rail, and this is called the toe. This is called the stock rail. It's a non-moving part of the switch. The two switch blades are fixed to each other by a stretcher bar to ensure that when one is against its stock rail, the other is fully clear and will provide room for the wheel flange to pass through cleanly. This is a crossing. It's the non-moving part of the switch and crossing layout that allows a train to pass in either direction once the switch has been set. This is the nose of the crossing. Either side of the crossing area, wing and check rails are provided to assist the guidance of the wheel sets through the crossing. Crossings can be either fabricated, made up of two machined rails joined together, or they can be cast as a single unit. Modern crossings are now cast from manganese steel, which is an advanced alloy that gets harder with use. This is an important property, as the nose of the crossing can take high impact loads as train wheels pass through.
My name's Lawrence Walton and I'm a graduate engineer working for Network Rail. I'm here today to teach you about switches and crossings. The most simple form of S&C is the turnout. This is a left-hand turnout. As you can see, it diverges from the main route in a leftward direction. This is how it works. In normal mode, the left-hand wheel rolls along the switch rail, and there's flangeway clearance for the right wheel to continue along the stock rail. The inside surface of the right flange is kept on course by the check rail. This restrains the wheel set and ensures it is directed along the correct route. Meanwhile, the left wheel transfers contact between the different parts of the crossing. That's where there's a high impact load. In the reverse, the right wheel rolls over the switch rail and follows its geometry. The inside surface of the left flange is guided by the check, forcing it to follow the stock rail on the new route. And the right-hand wheel makes a crossing, again impacting a load on the crossing nose.
There are many different types of switch and crossing on the network. They include turnouts, diamonds, crossovers, and slip diamonds. The type we use is determined by a number of factors, including the number of lines involved, frequency of use, and running line speed. Trains travelling at high speeds need long switches and crossings. At low speeds, such as in stations, trains can make tighter turns. Train movements across the network are set and controlled by signallers, who use switches to set routes for trains. Switches can be propelled by various devices. One of the simplest forms is a ground frame setup, a series of rods and cams attached to levers in signal boxes. these are now largely being replaced by remotely operated hydraulic and electromechanical devices.
Seen by rail sides all across the country. This is an HW2000 points machine. This is electromechanical. What we have here is your drive motor. To check the motor has done its job, over here we have an interlocking and detection system. Detection tells us when the points have completed their travel and locked. Locking holds the points in this state so they cannot be physically moved, so when a train runs over the top it remains in position. Facing point locks are one of the most important safety features on the S&C layout. They ensure that the points cannot be moved when set. This is important because failure to lock the switches could cause a derailment.
As engineers, we face an ongoing challenge to maintain and improve our switch and crossing assets. Trains can create large impact and lateral forces as they change course, and these forces can cause wear and deformation. Switches and crossings therefore have a limited lifespan before we need to replace them. Less than 5% of track miles are made up of switches and crossings, but over 17% of our maintenance budget is spent on them. We'll continue to research and develop new inspection techniques and material usage to increase their performance.
It's all about creating a network that's safe, reliable and efficient. It's what we do.